Tonight, we're going to explore something that seems like it should be the simplest thing in the universe. Take an electron, negatively charged. Take a proton, positively charged. Opposites attract. So push them together and you should get something neutral, right? But here's what actually happens when you force an electron into a proton. Both particles cease to exist. They don't just combine. They don't just stick together. They are fundamentally transformed into something entirely new. The electron vanishes. The proton vanishes. And in their place, a completely different particle appears, along with a ghostly messenger that carries the secret of what happened out into the cosmos. This process doesn't just happen in laboratories, it happens inside dying stars, and it helps trigger one of the most violent events in the universe. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let me start with something you already understand intuitively, even if you have never studied physics in your life. You know that magnets have two poles, a north and a south, and you know that opposite poles attract each other. If you hold two magnets with their opposite ends facing each other, you can feel them pulling together. You have to actively resist the pull to keep them apart. This same principle applies to electric charges. Positive attracts negative, negative attracts positive. It is one of the most basic rules in all of physics, and it works everywhere. It works in the static electricity that makes your socks cling together in the dryer. It works in the lightning that reaches down between the clouds and the ground during a storm. It works inside every atom of every object you have ever touched, every surface you have ever walked on, every breath of air you have ever taken. And it works between the two particles we are going to focus on tonight, the electron and the proton. These two particles are among the most important building blocks of the universe. Everything you see around you, the walls, the air, your own body, all of it is built from atoms. And at the heart of every atom, you find protons and electrons interacting through this simple rule. Positive attracts negative. The electron is one of the most fundamental particles in nature. It carries a negative electric charge, and it is extraordinarily small. In fact, as far as our most precise measurements can determine, the electron has no measurable physical size at all. It behaves as what physicists call a point particle, a mathematical point with mass and charge but no detectable diameter. Its mass is tiny, roughly 1/1836th the mass of a proton. That is like comparing a single grain of sand to a bowling ball. The electron is unimaginably light, and yet, this particle is responsible for nearly everything you interact with in daily life. The light you see is produced when electrons change energy levels inside atoms. The electricity running through the wires in your walls is a flow of electrons. The chemical bonds that hold molecules together, that hold your body together, are formed by electrons. The solidity of the floor beneath your feet exists because electrons in the atoms of the floor repel the electrons in the atoms of your shoes. Without electrons, the physical world as you experience it would not exist. The proton is different in almost every way. It sits at the center of the atom, deep inside the nucleus. It carries a positive electric charge, exactly equal in magnitude to the electron's negative charge, but opposite in sign. The proton is much heavier than the electron, roughly 1836 times heavier. And unlike the electron, the proton is not a point particle. It has a measurable size, a diameter of roughly 1 femtometer, which is 1 quadrillionth of a meter. That is unimaginably small by human standards, smaller than anything you could ever see even with the most powerful optical microscope. But it is still a real physical extent. The proton has structure, it is made of smaller things inside it. We will come back to that later because it turns out to be absolutely critical to our story. For now, what matters is this. The electron is negatively charged, the proton is positively charged, and opposite charges attract. So here is the obvious question. If positive and negative charges are drawn toward each other by one of the most powerful forces in nature, what happens when an electron encounters a proton? You might think they would crash together. You might think the negative charge would cancel the positive charge, and you would be left with something neutral, something with no charge at all. And in a sense, that is partly right. When a free electron encounters a free proton in space, the electromagnetic force pulls them toward each other. The electron falls into a bound state around the proton, settling into a specific energy level, and the result is a hydrogen atom. The simplest atom in the universe, 1 proton, 1 electron, bound together by electromagnetic attraction. This happens everywhere in the universe, constantly. Hydrogen is the most abundant element in the cosmos. It makes up roughly 75% of all the ordinary matter in the universe by mass. Every star, including our sun, began its life as an enormous cloud of hydrogen gas that collapsed under its own gravity and ignited nuclear fusion at its core. The vast clouds of gas drifting between the stars are mostly hydrogen. When the universe was young, just a few 100,000 years after the Big Bang, the cosmos cooled enough for electrons and protons to combine for the first time, forming hydrogen atoms. This event, which physicists call recombination, was one of the most important moments in cosmic history. Before recombination, the universe was a hot, dense fog, where light could not travel far before being scattered. After recombination, with electrons bound to protons in neutral atoms, light was finally free to stream across space. The universe became transparent. The afterglow of that moment, stretched and cooled by billions of years of cosmic expansion, is still detectable today as the cosmic microwave background radiation. So the electromagnetic force is extraordinarily effective at bringing electrons and protons together. It binds them into atoms. It holds those atoms together in molecules. It governs chemistry, biology, material science, and essentially everything in our everyday experience. But here is the crucial thing that most people never realize. The electromagnetic force can bring particles together. It can bind them. It can arrange them into astonishingly complex structures. But it cannot change what they are. This is a profound distinction, and it is at the heart of everything we are going to explore tonight. When an electron orbits a proton in a hydrogen atom, the electron is still an electron. The proton is still a proton. They have not changed. They have not transformed. They have not merged into something new. They are simply bound together, held in place by the electromagnetic attraction between their opposite charges. The electron keeps its negative charge, its tiny mass, its identity as an electron. The proton keeps its positive charge, its larger mass, its identity as a proton. Electromagnetism arranged them, but it did not alter them. Think of it like two people shaking hands. They are connected. They are interacting. But neither person has changed into someone else. The handshake does not merge them into a single new person. It simply connects two individuals who remain exactly who they were before. This is what electromagnetism does. It connects, it binds, it arranges, but it preserves identity with absolute rigidity. No electromagnetic interaction, no matter how strong, can turn an electron into something other than an electron or a proton into something other than a proton. Now, there is a third particle we need to meet, the neutron. The neutron sits inside the atomic nucleus alongside the proton. It has roughly the same mass as the proton, actually slightly heavier, but it carries no electric charge at all. It is electrically neutral, which is where its name comes from. The neutron was discovered in 1932 by the British physicist James Chadwick, and its discovery raised a fascinating question. The proton has a positive charge. The neutron has no charge. They are nearly identical in mass. They both live inside the nucleus. What exactly is the relationship between them? We now know that the proton and neutron are intimately related. They are like siblings in the same family. They are made of the same kinds of internal components, just arranged in a slightly different way. And here is the part that should grab your attention. Under the right circumstances, a proton can become a neutron, and an electron can be involved in making that happen. Not by simply orbiting the proton, not by just being attracted to it electromagnetically, but by participating in a process that destroys both the original electron and the original proton, and creates entirely new particles in their place. This is what we are building toward. The idea that forcing an electron into a proton under very specific conditions does not just bring them closer together, it fundamentally transforms them both. The electron does not get stuck inside the proton like a marble, pushed into a ball of clay. Both particles cease to exist, and new particles, a neutron and something called a neutrino, appear in their place. But to understand how this is possible, we first need to understand something deeper about the forces of nature. Because the electromagnetic force, powerful as it is, simply cannot perform this transformation. A completely different force is required. A force that most people have never heard of, but one that shapes the universe in ways few other forces can. Let us talk about the fundamental forces that govern everything in the universe, because understanding these forces is the key to understanding why an electron and a proton can be transformed into entirely new particles. Physics recognizes 4 fundamental forces of nature, just 4. These 4 interactions account for every physical phenomenon ever observed. They explain everything from the way galaxies cluster together across billions of light years, to the way an unstable atom breaks apart in a fraction of a second. They explain why the ground holds you up, why the sun shines, why your heart beats, and why certain atoms are radioactive. Every force you have ever felt, every interaction you have ever witnessed, traces back to one of these 4. The first force is gravity. Gravity is the one you know best. It is what keeps your feet on the ground. It is what keeps the Earth in orbit around the sun. It is what pulls the moon around the Earth and holds galaxies together across vast stretches of space. Gravity acts between anything with mass or energy, and it is always attractive. It never pushes things apart. It only pulls things together. But here is what might surprise you. Gravity is by far the weakest of the 4 fundamental forces, by an almost absurd margin. The gravitational attraction between a single proton and a single electron is roughly 10 to the 39th power times weaker than the electromagnetic force between them. That is a 1 followed by 39 zeros times weaker. To make that number feel real, imagine holding an electron above a proton and letting go. The electromagnetic force would yank that electron toward the proton so fast you could never perceive the motion. To replicate that same pull using only gravity, you would need to make the proton roughly 10 to the 39th power times more massive. An increase so extreme that no analogy can honestly capture it. That is how vast the gulf between these two forces is at the scale of individual particles. Gravity is so feeble at the scale of individual particles that physicists can completely ignore it when studying atoms and subatomic interactions. It simply does not matter at those scales. The only reason gravity seems powerful in your daily life is because the Earth is enormous. It contains roughly 10 to the 50th power atoms, all pulling on you simultaneously. Gravity wins through sheer, overwhelming numbers, not through individual strength, and here is what matters for our story. Gravity can crush stars, it can warp space-time, it can create black holes, but gravity cannot change what a particle is. A proton feeling gravity is still a proton. An electron falling in a gravitational field is still an electron. Gravity bends paths, it shapes orbits, it determines the large-scale structure of the cosmos. But it does not alter identity, not ever. So gravity is not the force we need. The second force is electromagnetism. This is the force we have already been discussing. It governs electric charges and magnetic fields. It is responsible for light, radio waves, X-rays, and every other form of electromagnetic radiation. It holds electrons in orbit around nuclei. It binds atoms into molecules. It makes chemistry and biology possible. Electromagnetism is vastly stronger than gravity at the particle scale. And unlike gravity, it can both attract and repel. Opposite charges attract. Like charges repel. This force is carried by particles called photons. When two charged particles interact electromagnetically, they exchange photons between them. These are not the same photons you see with your eyes. They are what physicists call virtual photons, messengers of the force that mediate the interaction without being directly observed. We've already seen the critical limitation. Electromagnetism cannot change the type of particle involved in the interaction. An electron interacting electromagnetically remains an electron, always. A proton interacting electromagnetically remains a proton, always. Electromagnetism can accelerate particles, bind them together, or push them apart. It can build the entire physical world you experience around you, but it preserves particle identities absolutely. No matter how violently you slam an electron and a proton together using electromagnetic force alone, the proton will never become a neutron, and the electron will never become anything other than an electron. Two forces examined. Two forces that cannot perform the transformation we need. Let us try the third. The third force is the strong nuclear force. This is the most powerful force in nature, but it operates only over incredibly short distances, roughly the width of an atomic nucleus, about 1 femtometer. Beyond that range, the strong force effectively vanishes. It drops away so sharply that at 2 or 3 femtometers, it is already negligible. This gives the strong force an almost paradoxical character. It is the mightiest force in existence, yet it is confined to the tiniest arena. Think about what exists inside an atomic nucleus. Protons and neutrons are packed incredibly close together. The protons all carry positive electric charges, which means they electromagnetically repel each other with tremendous force. Every proton in the nucleus is pushing away from every other proton. So why does the nucleus not fly apart? Because at these tiny distances, the strong force overwhelms the electromagnetic repulsion. At nuclear scales, the strong force is roughly 100 times more powerful than electromagnetism. It seizes the protons and neutrons and binds them together despite the furious electrical repulsion between the protons. The strong force also holds protons and neutrons themselves together internally. Remember, the proton has internal structure. It is made of smaller particles called quarks, bound together by carriers of the strong force called gluons. The name gluon literally comes from the word glue, because that is what they do. They glue quarks together inside protons and neutrons with a grip so powerful that quarks can never escape. If you tried to pull two quarks apart, the force between them would not weaken with distance the way gravity or electromagnetism does. It would stay constant or even increase. You would have to pour in so much energy that the energy itself would spontaneously create new quarks. The original quarks would never come free. This property is called confinement, and it is why isolated quarks have never been observed in nature. They are permanently imprisoned inside larger particles. So the strong force can grip particles with a ferocity that nothing else in the universe can match. It holds together the very heart of matter. Without it, no nucleus heavier than hydrogen could exist. No carbon, no oxygen, no iron, no planets, no life. The strong force is essential to everything material in the cosmos. And yet, for all its incredible power, the strong force shares the same fundamental limitation as electromagnetism and gravity. It cannot change what type of particle something is. The strong force holds quarks together, but it does not convert one type of quark into another. It holds protons and neutrons inside the nucleus with an iron grip, but it cannot turn a proton into a neutron or a neutron into a proton. It is like a chain, incredibly strong, unbreakable even, but a chain does not transform the objects it binds. It simply holds them in place. So now we have three forces. Gravity, which is far too weak to matter at particle scales and cannot change particle identity regardless. Electromagnetism, which can attract and bind particles but cannot change their identity. And the strong force, which can hold particles together with staggering power but also cannot change their identity. Three forces, three failures, each one supreme in its own domain, each one powerless to accomplish the specific task we need. It seems like nature has set up an impossible situation. We need a proton to become a neutron, but every tool we have examined so far is the wrong tool for the job. This brings us to the fourth and final force, the weak nuclear force. And this is where the story takes a turn. The weak force is misleadingly named. When people hear the word weak, they assume this force is unimportant, a minor footnote in the story of physics. That assumption could not be more wrong. The weak force is responsible for something that no other force in the universe can accomplish. It can change the fundamental identity of particles. It can transform one type of quark into another type of quark, and by doing so, it can turn a proton into a neutron, or a neutron into a proton. Electromagnetism cannot do this. The strong force cannot do this. Gravity cannot do this. Only the weak force possesses this extraordinary, singular ability. The weak force is called weak because at the distances where the strong force operates, it truly is weaker. Its strength at nuclear distances is roughly 10,000 to 100,000 times less than the strong force, and it operates over an even tinier range, about 1,000th the diameter of a proton. That is almost inconceivably small. You could live your entire life and never directly perceive the weak force at work, even though it is operating inside your own body right now. Certain isotopes of potassium in your bones and muscles are undergoing weak force-driven transformations at this very moment, as neutrons inside those atoms convert into protons and release radiation in the process. The weak force is carried by three massive particles: the W plus boson, the W minus boson, and the Z boson. These carriers are extraordinarily heavy compared to the photon, which carries the electromagnetic force and has no mass at all. The W bosons each have a mass roughly 80 times greater than the mass of a proton, and the Z boson is even heavier. This enormous mass is the reason the weak force has such a short range. Heavy carrier particles can only flicker into existence for the briefest of instants, before they must vanish again. And in that fleeting moment, they can only travel a minuscule distance. The heavier the carrier, the shorter the reach. The weak force was first theorized in the early 1930s, when the Italian physicist Enrico Fermi proposed a model to explain a mysterious phenomenon called beta decay. Beta decay is a process where an unstable atomic nucleus spontaneously emits an electron, or its antimatter counterpart, and transforms in the process. Fermi's model was brilliant for its time, but the full theory of the weak force would not be completed until decades later. In the 1960s and 70s, physicists Sheldon Glashow, Abdus Salam, and Steven Weinberg showed that the weak force and the electromagnetic force are actually two manifestations of a single underlying interaction, which they called the electro-weak force. At very high energies, the kind of energies that existed in the first fractions of a second after the Big Bang, these two forces are indistinguishable. They are the same force. It is only at the lower energies of our everyday universe that they appear different. This unification was one of the greatest achievements in 20th century physics and earned all three scientists the Nobel Prize in 1979. But the key point for our story, the reason we've spent this time talking about forces, is this. The weak force can do something unique. It can change the flavor of quarks. Flavor is the term physicists use for the different types of quarks. There are 6 flavors in total, but the 2 that matter for us tonight are called up and down. A proton contains 2 up quarks and 1 down quark. A neutron contains 1 up quark and 2 down quarks. That is the only structural difference between them. The difference between a proton and a neutron, the difference between a positively charged particle and a neutral one, comes down to a single quark being up instead of down. The weak force can reach inside a proton and change one of its up quarks into a down quark. When that happens, the proton is no longer a proton. It has become a neutron. 2 up quarks and 1 down have become 1 up quark and 2 down. The particle's identity has changed. Its charge has changed. It has been fundamentally transformed. No other force can do this. Electromagnetism cannot reach inside a proton and rearrange its quarks. The strong force holds those quarks together, but does not alter them. Only the weak force can perform this act of particle alchemy. And this is precisely why the electromagnetic force, despite all its ability to attract an electron toward a proton, can never merge them into a neutron on its own. Electromagnetism can pull the electron close, it can bind the electron into a hydrogen atom. but it cannot reach inside the proton and flip a quark. That is not what electromagnetism does. To turn a proton into a neutron, you must change one of its internal quarks. And to change an internal quark, you need the weak force. There is no shortcut. There is no workaround. The weak force is the only doorway through which this transformation can pass. But there is a problem. A serious problem that nature enforces with absolute authority. And understanding this problem is the key to understanding why this transformation does not simply happen everywhere, all the time, whenever electrons and protons happen to be near each other. A neutron is heavier than a proton and an electron combined. Not by a lot, but by enough to matter. The difference is small in absolute terms, roughly 1/7 of 1% of the proton's total mass. But in the world of particle physics, this tiny difference is everything. Because of Einstein's famous equivalence between mass and energy, creating a particle with more mass requires energy. You cannot produce something heavier from something lighter without supplying additional energy from somewhere. This is not a guideline. It is not a suggestion. It is a law. The conservation of energy is one of the most rigorously tested principles in all of physics. It has never been observed to be violated, not once, not under any circumstances, not even for an instant. This means that a free electron and a free proton, drifting through empty space with no additional energy source, cannot spontaneously combine to form a neutron. The combined mass of the electron and proton is less than the mass of the neutron they would need to create. The energy simply is not there. It is like trying to buy something that costs more than you have in your pocket. The transaction cannot go through. Nature keeps an absolutely perfect energy ledger, and there is no borrowing, no credit, no exceptions, and no delays. So we arrive at a paradox. The electromagnetic force can attract the electron and proton together, but it cannot transform them. The weak force can transform them, but the transformation costs more energy than the two particles possess on their own. It seems like this reaction should be flatly impossible. And between a lone electron and a lone proton floating freely in empty space, it is impossible. Under those conditions, when an electron meets a proton, you simply get hydrogen, a stable atom. Nothing dramatic, nothing transformative, just the simplest atom in nature, formed through the most ordinary of electromagnetic interactions. But the universe is not always ordinary. There are places where conditions become so extreme that the energy equation changes completely. Inside certain atomic nuclei, the proton is not free, it is bound together with other protons and neutrons, and the binding energy of that nucleus can supply the missing energy that makes the transformation possible. And in the crushing cores of dying massive stars, electrons are squeezed to such extraordinary energies by the sheer pressure of gravity that they carry more than enough energy to force the conversion. In those environments, what seemed impossible becomes not only possible, but unstoppable. And when it happens, when this quiet quantum transformation occurs trillions upon trillions of times inside a collapsing star, the consequences are among the most violent and spectacular events the universe has ever produced. So now we know the setup. Electromagnetism can attract an electron toward a proton, but it cannot transform either particle into something else. Only the weak nuclear force possesses that ability, and the transformation costs energy because the neutron that would be created is heavier than the electron and proton combined. Between two free particles drifting in empty space, this reaction simply cannot occur. But let us set aside the energy problem for now. We will come back to it in detail later when we explore the specific environments where that energy becomes available. For the moment, let us focus on something equally important. When this transformation does happen, when conditions allow it, what exactly takes place? What is the actual mechanism? How does an electron and a proton become a neutron? Because the answer is far stranger, far more subtle, and far more beautiful than most people ever imagine. Let us walk through it step by step. Imagine a proton and an electron in close quarters, not just electromagnetically bound in a hydrogen atom, but genuinely close. Close enough that the weak force, which operates only over distances roughly 1,000th the diameter of a proton, can come into play. At these extraordinarily tiny distances, something becomes possible that is impossible at any greater range. The weak force can mediate an exchange between the electron and one of the quarks inside the proton. Remember from earlier that a proton is not a featureless ball. It has internal structure. It is made of 3 quarks, 2 up quarks, and 1 down quark, bound together by gluons. These quarks are not sitting still inside the proton. They are in constant furious motion, buzzing around at significant fractions of the speed of light, exchanging gluons with each other in a seething storm of strong force interactions. The interior of a proton is one of the most violent environments in the universe at the subatomic scale. But despite all that violence, the quarks maintain their identities. The strong force holds them together. It does not alter them. 2 up quarks and 1 down quark. That is a proton. It stays a proton as long as nothing else intervenes. Now the electron arrives. It gets close enough for the weak force to act. And here is what happens. The electron interacts with one of the up quarks inside the proton through the exchange of a W- boson. This is the messenger particle of the weak force, the carrier that makes the transformation possible. The W- boson is extraordinarily heavy, roughly 80 times the mass of the proton itself. You might wonder how such a massive particle can appear at all when the electron and the quark involved are so much lighter. The answer lies in one of the strangest aspects of quantum mechanics, the Heisenberg uncertainty principle. The Heisenberg uncertainty principle tells us that energy can fluctuate on extremely short timescales. The shorter the time interval, the larger the energy fluctuation that nature permits. Over fantastically brief moments, durations so short that no clock could ever measure them. Enough energy can momentarily become available for an extremely massive particle to flicker into existence. But this particle must vanish again almost immediately. It cannot persist. It cannot travel far. It exists only as a fleeting intermediary, a virtual particle that carries force and information from one real particle to another before disappearing. The W- boson that mediates this interaction is exactly such a particle. It appears for an inconceivably brief instant, far less than a billionth of a billionth of a billionth of a second. And in that moment, it accomplishes something remarkable. The W- boson carries electric charge. Specifically, it carries 1 unit of negative charge. When the electron emits this W- boson, the electron ceases to exist as an electron. It does not shrink. It does not hide. It does not tuck itself inside another particle. It genuinely transforms. The electron's identity, its properties, its very existence as what we call an electron, all of it is converted in this interaction. In the electron's place, a different particle emerges, a neutrino, specifically an electron neutrino. We will talk much more about this ghostly particle in a moment. Meanwhile, the W- boson, carrying its negative charge, reaches the up quark inside the proton. The up quark absorbs the W- boson, and when it does, the up quark changes. It transforms from an up quark into a down quark. This is the key moment. This is the transformation that no other force in the universe can produce. The strong force was holding the quarks together the entire time, but it could not change them. Electromagnetism was present, doing what it always does, but it could not change them. Only the weak force, acting through this fleeting W- boson, could reach in and flip that quark from one type to another. The proton contained 2 up quarks and 1 down quark. Now, after the absorption of the W- boson, one of those up quarks has become a down quark. The particle now contains 1 up quark and 2 down quarks. That is no longer a proton. That is a neutron. The proton has ceased to exist. In its place, a neutron has been born. So the full transformation looks like this. An electron and a proton go in. A neutron and an electron neutrino come out. The original particles are gone. They have not been stored somewhere. They have not been hidden. They have been genuinely, irreversibly transformed into 2 entirely different particles. This reaction is called electron capture, and it is one of the most fundamental processes in nuclear physics. Let me be very clear about something, because this is a point where misconceptions easily arise. The neutron that results from this process does not contain an electron trapped inside it. This is an easy mistake to make. You might think that the electron simply got pushed into the proton, that it is sitting inside the neutron like a ball stuffed into a bag. That picture is completely wrong. The neutron is made of 1 up quark and 2 down quarks, bound together by gluons. There is no electron inside it. The electron's charge, the electron's mass, the electron's very identity have been absorbed into the transformation. The electron contributed to the process. Its charge balanced the books. Its energy helped fuel the reaction. But it is gone. It no longer exists in any form inside the neutron. Think of it this way. If you burn a piece of wood, you get ash, smoke, and heat. The wood is gone. You cannot find the wood inside the ash. The wood was not stored in the ash. It was transformed. The atoms that made up the wood have been rearranged into entirely different molecules. The wood as an object no longer exists. Similarly, the electron and proton as individual particles no longer exist after electron capture. Their properties have been redistributed into the neutron and the neutrino. The transformation is genuine and complete. Now, let us talk about the neutrino, because this particle is one of the most extraordinary objects in all of physics, and its role in this reaction is absolutely essential. The neutrino was first proposed theoretically in 1930 by the Austrian physicist Wolfgang Pauli. At the time, physicists were studying a process called beta decay, where certain unstable atomic nuclei emit electrons. But there was a problem. When they carefully measured the energy of the emitted electrons, the numbers did not add up. The electrons came out with a range of energies, sometimes more, sometimes less. But the energy difference between the original nucleus and the final nucleus was always the same fixed amount. If the electron was the only particle emitted, it should always carry exactly that fixed amount of energy. Instead, the energy seemed to be split between the visible electron and something invisible. Some physicists at the time, including the great Niels Bohr, seriously considered the possibility that energy conservation might be violated in these reactions. that energy might simply not be conserved at the subatomic level. This would have been a revolutionary and deeply unsettling conclusion. But Pauli proposed a different explanation. He suggested that a second, invisible particle was being emitted alongside the electron. This unseen particle would carry away the missing energy, accounting for the variable energy of the electrons without violating energy conservation. Pauli called this hypothetical particle a little neutral one, and the Italian physicist Enrico Fermi later gave it the name Neutrino. For over 2 decades, the neutrino remained a theoretical prediction. Many physicists doubted it could ever be detected because its properties made it almost impossibly elusive. The neutrino has no electric charge, so the electromagnetic force ignores it completely. It has an incredibly tiny mass, so small that for decades, physicists thought it might be exactly zero. And the neutrino interacts only through the weak force and gravity, both of which are extraordinarily feeble at the relevant scales. This means a neutrino can pass through matter almost without any interaction at all. How ghostly is the neutrino? Consider this. Right now, as you listen to these words, roughly 65 billion neutrinos from the sun are passing through every square centimeter of your body every single second. They are streaming through you, through the walls around you, through the entire planet, and out the other side without touching a single atom. The Earth itself is essentially transparent to neutrinos. A neutrino produced in the core of the sun can fly through a wall of solid lead a light year thick and still have a better than even chance of emerging from the other side without hitting anything. The neutrino is the ultimate ghost particle. It is there, it carries real energy and real momentum, but it barely interacts with anything. In 1956, American physicists Clyde Cowan and Frederick Reines finally detected neutrinos directly, using a nuclear reactor as a source. The experiment was extraordinarily difficult precisely because neutrinos interact so weakly with matter. Out of the trillions of neutrinos streaming from the reactor every second, Cowan and Reines detected roughly 3 per hour. 3 out of trillions. That is how ghostly these particles are. The discovery earned Reines the Nobel Prize in Physics in 1995, decades after the experiment. Cowan had passed away by then and could not share in the award. In the electron capture reaction, the neutrino that emerges is specifically an electron neutrino. This distinction matters because there are actually 3 types of neutrinos in nature, each associated with a different family of particles. The electron neutrino is paired with the electron. It appears whenever the weak force involves an electron, and it must appear. Its emission is not optional. It is required by a conservation law that is just as inviolable as the conservation of energy. This law is called the conservation of lepton number. Let me explain what lepton number means because it is central to understanding why the neutrino must be emitted. In particle physics, certain quantities are conserved in every interaction. These are like cosmic accounting rules that the universe never breaks. You have encountered some of these already. Conservation of energy says that the total energy before a reaction must equal the total energy after the reaction. Conservation of electric charge says that the total charge before a reaction must equal the total charge afterward. These are absolute rules. No exceptions have ever been observed. Let us check the charge balance in electron capture. Before the reaction, we have an electron with a charge of -1 and a proton with a charge of +1. The total charge is -1 plus +1, which equals 0. After the reaction, we have a neutron with a charge of 0 and an electron neutrino with a charge of 0. The total charge is 0 plus 0, which equals 0. 0 before, 0 after. Charge is conserved. The books balance perfectly. Now let us look at energy and momentum. Conservation of energy requires that the total energy before and after the reaction must be equal. Conservation of momentum requires that the total momentum before and after must also be equal. In practice, this means the kinetic energy and momentum carried by the incoming electron, combined with the mass energy of both the electron and proton, must exactly account for the mass energy of the neutron, plus whatever kinetic energy and momentum the neutron and neutrino carry away. The neutrino plays a critical role here. It carries away energy and momentum that would otherwise be unaccounted for. Without the neutrino, the energy and momentum books would not balance. The neutron alone cannot simultaneously satisfy both conservation of energy and conservation of momentum. The neutrino provides the extra degree of freedom needed to make both conservation laws work at the same time. But there is another conservation law at play, one that is less well known, but equally absolute. This is the conservation of lepton number. Leptons are a family of particles that includes the electron, the muon, the tau particle, and their corresponding neutrinos. Each lepton is assigned a lepton number of +1. Each antilepton, the antimatter counterpart of a lepton, is assigned a lepton number of -1. Particles that are not leptons, such as protons, neutrons, and quarks, have a lepton number of 0. The rule is simple. The total lepton number before a reaction must equal the total lepton number after. Before the electron capture reaction, we have an electron, which is a lepton with lepton number +1. And we have a proton, which is not a lepton and has lepton number 0. The total lepton number before the reaction is +1. After the reaction, we have a neutron, which is not a lepton and has lepton number 0. If the neutron were the only product, the total lepton number after the reaction would be 0. But 0 does not equal +1. The lepton number would not be conserved. The reaction would be forbidden. This is precisely why the neutrino must be emitted. The electron neutrino is a lepton with lepton number +1. When the neutron with lepton number 0 and the electron neutrino with lepton number +1 are produced together, the total lepton number after the reaction is 0 plus 1, which equals +1. That matches the lepton number before the reaction. The books balance, the law is satisfied. Without the neutrino, electron capture would violate the conservation of lepton number. And the universe does not allow that, not ever, not under any circumstances. The neutrino is not an incidental byproduct of this reaction. It is a mandatory product, required by one of the deepest conservation laws in physics. Whenever the weak force transforms an electron into something else, the universe demands that an electron neutrino emerge to preserve the lepton number. The electron's leptonic identity, if you will, must be carried forward even though the electron itself no longer exists. The neutrino inherits that identity. Let me now address a question that might be forming in your mind. If a W- boson is exchanged and it is so incredibly massive, where does the mass come from? This is a subtle but important point. The W- boson that mediates this interaction is what physicists call a virtual particle. It does not obey the normal relationship between energy and mass that real, observable particles must satisfy. A real W- boson one that you could detect in a particle accelerator, has a mass of roughly 80 times the proton mass. Creating such a particle for real would require an enormous amount of energy. But a virtual W boson does not need all that energy because it does not exist as a real, detectable particle. It exists only as a mathematical entity describing the transfer of force between two particles, and it exists for such an inconceivably short time that the uncertainty principle permits this temporary violation of the energy-mass relationship. This is one of the deepest and most counterintuitive aspects of quantum mechanics. At very short timescales, the universe allows what would seem like violations of energy conservation, but only if they are resolved quickly enough. The W boson flickers in and out of existence so rapidly that the energy borrowing is repaid before the universe can notice. This is not a loophole or a trick. It is a fundamental feature of how quantum fields work. It is the reason the weak force can operate at all at the energies found inside ordinary atoms, even though the W boson is enormously heavy. The carrier does not need to be produced as a real particle. It only needs to exist as a virtual intermediary for the briefest of instants. Now, let me step back and describe the entire process again, from beginning to end, as one continuous sequence, because seeing the full flow of events is important for grasping the elegance of what nature accomplishes here. An electron approaches a proton. The electromagnetic force has been pulling them toward each other, but electromagnetism alone cannot do what happens next. The electron gets close enough, within roughly 1,000th of a femtometer, for the weak force to act. In this vanishingly small region of space, a W- boson is exchanged. The electron emits this virtual W- boson, and in doing so, the electron is transformed into an electron neutrino. The electron ceases to exist. Its charge has been transferred to the W- boson. Its lepton number has been passed to the neutrino. The W- boson, carrying negative charge, is absorbed by an up quark inside the proton. The up quark absorbs the W- boson and transforms into a down quark. The proton, which was 2 up quarks and 1 down quark, is now 1 up quark and 2 down quarks. It is no longer a proton, it is a neutron. The neutrino, carrying energy, momentum, and lepton number, flies away from the interaction at nearly the speed of light. It will pass through almost anything in its path without stopping. 2 particles went in, 2 different particles came out. Total electric charge is conserved. 0 before, 0 after. Total lepton number is conserved. 1 before, 1 after. Total energy is conserved, provided enough energy was available to create the heavier neutron. Total momentum is conserved, shared between the neutron and the escaping neutrino. Every single conservation law is obeyed. Nothing is violated, nothing is cheated, nothing is borrowed without repayment. The universe's books are in perfect balance after the transaction, just as they were before, but the physical reality has changed completely. 2 familiar particles, an electron and a proton, are gone. 2 entirely different particles, a neutron and a neutrino, have taken their place. This is not a minor rearrangement. This is a transformation at the deepest possible level. The fundamental nature of the matter involved has changed, and notice what has not happened. The proton did not simply swallow the electron whole. The electron is not hiding inside the neutron. If you could examine a neutron with unlimited precision, you would find 1 up quark, 2 down quarks, and a cloud of gluons holding them together. You would not find an electron anywhere. The neutron is its own particle, with its own identity, its own internal structure, and its own properties. It was born from the transformation, but it does not contain the raw ingredients of the transformation within it. The electron and proton were consumed, their properties redistributed, and conserved through the products of the reaction. The electron's charge cancelled the proton's charge, producing a neutral neutron. The electron's lepton number was carried away by the neutrino. The combined energy of the electron and proton was redistributed among the neutron and the neutrino, accounting for the neutron's higher mass and the kinetic energy of both products. This process, this quiet, invisible, almost instantaneous transformation, is happening right now in laboratories, in hospitals, in the Earth's crust, and in the cores of stars. It happens every time a particular kind of unstable atomic nucleus adjusts itself towards stability. And it happens on a massive, almost incomprehensible scale inside the collapsing cores of dying stars, where the consequences are not quiet at all. But there is something deeply striking about electron capture that deserves a moment of reflection. The process is driven by the weakest of the forces capable of producing it. Not by the enormously powerful strong force, not by the familiar electromagnetic force, by the weak force, the one whose carriers are so massive they can barely reach across 1,000th of a proton's width. And yet, this seemingly feeble interaction reshapes the identity of matter itself. It does something that brute strength cannot accomplish. Gravity, with all its ability to crush stars and bend light, cannot change a quark's flavor. The strong force which binds nuclei together against ferocious electromagnetic repulsion cannot flip an up quark into a down quark. But the weak force can, quietly, subtly, over distances so small that they make atoms look like galaxies by comparison. There is a lesson in that. Sometimes the most transformative power is not the most forceful. Sometimes it is the most subtle. Now we have described the mechanism. We have described the conservation laws. We have described the products. But we have deliberately avoided a crucial question. The question we set aside at the beginning. Where does the energy come from? Because a neutron is heavier than a proton and an electron combined. And without that extra energy, the reaction simply will not happen. No amount of closeness, no amount of weak force cleverness can overcome the basic arithmetic of energy conservation. If the energy is not available, the transformation is forbidden. So the question becomes, where in the universe can this energy be found? Where are the environments extreme enough, or the nuclear configurations special enough, to provide the missing energy that the free particles alone cannot supply? The answer to that question will take us inside the nuclei of unstable atoms, and then into the crushing hearts of the most massive dying stars in the cosmos. And what we find there will show us that this quiet, microscopic transformation, this little quark flip mediated by a fleeting virtual boson, has consequences that reach across the entire cosmos. We have now seen the mechanism. We know exactly how the weak force reaches inside a proton, flips an up quark into a down quark, and transforms the proton into a neutron, while converting the electron into a neutrino. The conservation laws are satisfied. The physics is sound. The process is elegant. But there is a wall standing in the way. A wall that nature built out of the most unbreakable law in physics. The conservation of energy. A neutron is heavier than a proton, not by a dramatic amount, but by enough to matter enormously. The mass difference between a neutron and a proton is about 1.293 mega-electron volts of energy, expressed through Einstein's famous relationship between mass and energy. E equals mc squared tells us that mass and energy are the same thing, just in different forms. Any particle with mass contains energy simply by existing. A heavier particle contains more of this rest mass energy than a lighter particle, and a neutron contains more rest mass energy than a proton. Now, the electron also has mass. Its rest mass energy is about 0.511 mega electron volts. So when you add the proton's mass and the electron's mass together, you get a total that is still less than the neutron's mass. The neutron outweighs the proton and electron combined by about 0.782 mega electron volts. That might sound like a tiny number, and in everyday terms it is. But in the world of nuclear and particle physics, it is an enormous barrier. Let me put this in concrete terms. If you have a free proton and a free electron sitting in empty space, at rest, with no external energy source, the total mass energy of the system is the proton's mass energy plus the electron's mass energy. That total is less than the mass energy of a single neutron. To create a neutron from these two particles, you would need to conjure additional energy from somewhere, roughly 0.782 mega electron volts of it, and add it to the system. But in empty space, with no external input, that energy does not exist. There is nothing to supply it. This is why a lone electron and a lone proton do not spontaneously merge into a neutron. It is not because the weak force is too feeble to perform the transformation. It is not because the particles cannot get close enough. It is because creating a neutron would require more energy than the two free particles possess. The transaction cannot go through because the cost exceeds the available funds. Nature's energy ledger is absolute. You cannot create mass from nothing. You cannot borrow energy that will never be repaid. The law is ironclad, and it has never been observed to fail. So when an electron encounters a proton under ordinary conditions in the vacuum of space, what happens is simple and familiar. The electromagnetic force pulls them together, and they form a hydrogen atom. The electron settles into a quantum orbital around the proton. The system releases a small amount of energy, typically in the form of a photon, as the electron drops into its bound state. And that is the end of the story. The proton remains a proton. The electron remains an electron. They are bound together electromagnetically, but neither has changed into anything else. No neutron is formed. No neutrino is emitted. No weak interaction occurs. Just a perfectly ordinary, perfectly stable hydrogen atom. The simplest atom in the universe. This is the normal outcome when an electron meets a proton. And it is profoundly important that we understand this before moving forward. The transformation we described earlier, electron capture, is not the default. It is not what normally happens. Under ordinary circumstances, electrons and protons simply form atoms. The dramatic transformation into a neutron and a neutrino requires special conditions. Conditions that provide the missing energy. So where does the energy come from? The first answer, and the one that plays out in laboratories and hospitals and the Earth's crust every day, involves the atomic nucleus itself. To understand this, we need to talk about nuclear binding energy. This concept is the key that unlocks the entire mystery of electron capture in atoms. And it is one of the most important ideas in all of nuclear physics. When protons and neutrons come together to form an atomic nucleus, something remarkable happens. The total mass of the assembled nucleus is less than the combined masses of all the individual protons and neutrons that compose it. Hear that again, because it sounds impossible. If you take, say, 4 protons and 4 neutrons and weigh them individually, then assemble them into a nucleus, the nucleus weighs less than the sum of its parts. Mass has apparently vanished. Where did it go? It went into energy. Specifically, it became the binding energy that holds the nucleus together. When protons and neutrons snap together under the powerful grip of the strong nuclear force, energy is released. And because mass and energy are equivalent, the released energy corresponds to a decrease in mass. The nucleus is lighter than the sum of its parts by exactly the amount of energy that was released when it formed. This energy would have to be supplied back to the nucleus to break it apart again. The more binding energy a nucleus has, the more tightly its protons and neutrons are held together, and the more stable it is. Different nuclei have different amounts of binding energy per particle. This is crucial. Not all nuclei are equally tightly bound. Some are very tightly bound, meaning a lot of energy was released when they formed, and a lot of energy would be needed to break them apart. Others are less tightly bound, meaning less energy was released during formation, and less energy would be needed to pull them apart. Iron 56 sits at the peak of the nuclear binding energy curve. It is among the most tightly bound nuclei in nature. It sits at the bottom of the nuclear energy valley. Nuclei lighter than Iron 56 can release energy by fusing together, which is what powers stars. Nuclei heavier than Iron 56 can release energy by splitting apart, which is what happens in nuclear fission and in the decay of radioactive elements. Iron 56 is the endpoint, the most stable configuration that nuclear matter can achieve. Now, here is where everything comes together. Imagine an unstable atomic nucleus that contains too many protons relative to neutrons for its particular position in the chart of nuclei. Such a nucleus is not sitting at its lowest possible energy state. It could become more stable, more tightly bound, if one of its protons were converted into a neutron. The resulting daughter nucleus would have higher binding energy per particle than the parent nucleus. It would be more stable. And this is where the energy comes from. Remember, converting a free proton into a neutron requires extra energy because the neutron is heavier. But inside a nucleus, the situation is different. The parent nucleus and the daughter nucleus have different binding energies. If the daughter nucleus is sufficiently more tightly bound than the parent, the difference in binding energy can be large enough to compensate for the mass difference between the proton and the neutron. The energy that was locked up as less than optimal binding in the parent nucleus gets released during the transformation, and this released energy pays the cost of creating the heavier neutron. Think of it like this. Imagine you are on a hilltop and there is a valley below you. Rolling a heavy boulder up a small bump would normally require energy you do not have. But if you are already on a hilltop, you can roll the boulder downhill and use the energy of the descent to push it over the small bump on the way down. The bump is still there, it still requires energy to cross, but the energy of the descent provides it. The parent nucleus is on the hilltop, the daughter nucleus is in the valley. The mass difference between the neutron and the proton plus electron is the bump. And the difference in nuclear binding energy between the parent and daughter is the hill that provides the energy to get over the bump. Let me give you a specific example. Beryllium-7 is an unstable isotope of beryllium. Its nucleus contains 4 protons and 3 neutrons. This nucleus is proton-rich, meaning it has more protons than would be ideal for maximum stability. Beryllium-7 can become more stable by converting one of its protons into a neutron. The result would be a nucleus with 3 protons and 4 neutrons, which is lithium-7. And lithium-7 happens to be a very stable nucleus, much more tightly bound than beryllium-7. Here is what happens. An inner orbital electron from the beryllium-7 atom gets close to the nucleus, close enough for the weak force to act. The electron interacts with one of the protons through the exchange of a virtual W- boson. The electron is transformed into an electron neutrino. The proton is transformed into a neutron. The beryllium-7 nucleus has become a lithium-7 nucleus. The binding energy of lithium-7 is sufficiently greater than the binding energy of beryllium-7 that the difference more than covers the mass gap between the neutron and the proton plus electron combination. The excess energy goes into the kinetic energy of the neutrino and a small recoil of the lithium-7 nucleus. Energy is perfectly conserved, no laws are broken, the reaction proceeds spontaneously because the final state has less total mass energy than the initial state once you account for the nuclear binding energy differences. Beryllium-7 has a half-life of about 53 days. This means that if you start with a collection of beryllium-7 atoms, roughly half of them will have undergone electron capture within 53 days. This is not a particularly fast process by human standards, but it is inevitable. Every single beryllium-7 atom will eventually capture one of its own electrons and transform into lithium-7. The process cannot be stopped by any chemical or physical means. You cannot prevent it by changing the temperature, the pressure, or the chemical environment. The weak force operates inside the nucleus, beyond the reach of chemistry. It is a nuclear process, and nuclear processes are essentially immune to the conditions that affect ordinary chemical reactions. This specific reaction, beryllium-7 capturing an electron to become lithium-7, actually plays a role in the nuclear reactions that power our sun, deep in the solar core, where hydrogen is being fused into helium through a complex chain of reactions. Beryllium-7 is produced as an intermediate step. Some of that beryllium-7 captures an inner electron and transforms into lithium-7, releasing a neutrino in the process. These solar neutrinos stream outward from the core and eventually reach Earth, where sensitive detectors deep underground can occasionally catch one. Detecting these specific neutrinos tells us directly about the nuclear reactions happening in the heart of the Sun. It is one of the most remarkable achievements of modern physics, using ghost particles to peer inside a star. Now, let us look at another example that is closer to home. Potassium-40 is a naturally occurring radioactive isotope found everywhere on Earth. It is present in the soil, in rocks, in the food you eat, and in your own body. Potassium is an essential nutrient. Your muscles and nerves depend on it to function properly, and a tiny fraction of the potassium in your body, roughly 0.012%, is the radioactive isotope potassium-40. Potassium-40 is unstable. It has too many protons relative to its neutron count for optimal stability, and one of the ways it decays is through electron capture. A proton in the potassium-40 nucleus captures an inner orbital electron, transforms into a neutron, and emits an electron neutrino. The result is argon-40, a stable noble gas. Potassium-40 as a whole has a half-life of roughly 1.25 billion years, with roughly 1 in every 9 of those decays following the electron capture path to argon-40. That is extraordinarily slow. It means that potassium-40 atoms are patient. They wait for enormous spans of time before decaying. But over geological timescales, this process has profound consequences. The argon-40 produced by this decay accumulates in rocks and minerals. Geologists use the ratio of potassium-40 to argon-40 in rocks to determine their age. This technique, called potassium-argon dating, is one of the primary methods scientists use to determine the age of ancient rocks, volcanic deposits, and even the timing of early human evolution. One of the most famous applications of this technique involved the volcanic ash layers at La Etoli in Tanzania, where in 1978, the paleoanthropologist Mary Leakey discovered a trail of ancient hominin footprints preserved in hardened volcanic ash. The footprints were clearly made by beings who walked upright on two legs. But how old were they? The answer came from potassium-argon dating. Scientists measured the ratio of potassium-40 to argon-40 in the volcanic ash that covered and surrounded the footprints. The quiet accumulation of argon-40 atoms, each one produced by a single electron capture event inside a single potassium-40 nucleus, told them the ash was roughly 3.6 million years old. 3.6 million years of quark flips, recorded in the ratio of 2 isotopes. That is how scientists determined that upright walking in our ancestors began far earlier than anyone had previously imagined. A quantum process operating one atom at a time inside volcanic minerals became the clock that rewrote the story of human origins. This same weak force transformation is one of the tools scientists use to read the geological history of our planet. And here is a detail that often surprises people. Right now, at this very moment, potassium-40 atoms in your body are undergoing electron capture. Protons are being transformed into neutrons inside your own bones and muscles. Neutrinos are being produced and are streaming out of your body at nearly the speed of light, passing through the walls and the floor and the earth itself without interacting with anything. You are at this very moment a source of neutrinos. Your body is performing the same fundamental weak force transformation that occurs in the cores of stars. The same physics, the same mechanism, the same quark flip, just happening quietly, one atom at a time, inside you. Let me give you one more example that illustrates a different aspect of electron capture. Nickel-56 is an isotope that is produced in enormous quantities during certain types of supernova explosions. It is radioactive and decays through electron capture. A proton in the nickel-56 nucleus captures an electron and becomes a neutron, transforming the nucleus into cobalt-56. Cobalt-56 is also unstable and eventually decays further. The chain of decays from nickel-56 through cobalt-56 produces gamma rays, high-energy photons that heat the expanding cloud of debris from the supernova. This heating is what makes supernova remnants glow for weeks and months after the initial explosion. The light curves of certain supernovae, the way their brightness changes over time, are directly shaped by the rate of electron capture in nickel-56 and the subsequent decay of cobalt-56. Astronomers can measure these light curves from billions of light years away and use them to determine how much nickel-56 was produced in the explosion. Electron capture, this quiet quantum process, literally determines how brightly a dead star shines across the cosmos. Now, let me draw a sharp distinction that is essential for clarity. Because electron capture and ordinary hydrogen formation are two completely different processes, and confusing them would lead to a fundamentally wrong understanding of what is happening. When a free electron and a free proton meet in ordinary conditions, the electromagnetic force binds them into a hydrogen atom. The electron orbits the proton. Both particles retain their identities. No weak interaction occurs. No neutron is formed. No neutrino is emitted. The electron and proton remain exactly what they were. They are simply bound together. This is an electromagnetic process, and it happens everywhere in the universe, all the time, producing the most common element in the cosmos. Electron capture is entirely different. In electron capture, the electron does not merely orbit the proton. The electron is consumed. It ceases to exist. The proton is also consumed. It ceases to exist. Both are transformed into new particles, a neutron and a neutrino, through a weak force interaction. This process requires the involvement of the weak nuclear force, which is the only force capable of changing quark flavors. And it requires sufficient energy to create the heavier neutron, energy that in atomic electron capture comes from the difference in nuclear binding energy between the parent and daughter nuclei. These are not two versions of the same process. They are fundamentally different interactions governed by different forces, producing different outcomes, and operating under different conditions. Hydrogen formation is electromagnetic and preserves particle identity. Electron capture is a weak interaction and destroys particle identity, creating entirely new particles. The only similarity is that both involve an electron and a proton. Everything else about them is different. This distinction matters because it tells us something deep about how the universe works. The electromagnetic force which dominates our everyday experience is a conservative force in the sense that it conserves particle identity. It rearranges particles, it binds them and unbinds them, but it never transforms them. The weak force is fundamentally different. It is the only force that can change what a particle is at the most basic level. This makes the weak force unique among all the forces of nature. It is the agent of transmutation, the alchemist of the subatomic world. Let me also clarify something about which electrons can be captured. In atomic electron capture, the electron that gets captured is typically an inner orbital electron, one that spends a significant amount of time near the nucleus. In the quantum mechanical description of the atom, electrons do not orbit the nucleus in neat circles like planets around a star. Instead, they exist in probability clouds called orbitals. These orbitals describe the likelihood of finding the electron at various distances from the nucleus. Some orbitals bring the electron very close to the nucleus. The innermost orbital, called the 1s orbital, actually has a non-zero probability density right at the center of the nucleus. This means there is a small but real chance of finding the electron inside the nucleus at any given moment. It is this overlap between the electron's probability cloud and the volume of the nucleus that makes electron capture possible. The electron does not need to be fired at the nucleus like a bullet. It does not need to tunnel through a barrier. It simply needs to exist in a quantum state where its probability cloud overlaps with the nuclear volume. When it does, there is a chance at each moment that the weak force will act. The W- boson will be exchanged, and the transformation will occur. The probability is small at any given instant, but over time, for an unstable nucleus, it becomes a certainty. The cumulative probability grows until eventually the capture happens. This quantum mechanical overlap is why electron capture is sometimes called a nuclear decay mode rather than a collision process. The electron is not colliding with the nucleus in the classical sense. It is already there, in a quantum mechanical sense, by virtue of its orbital. It is part of the same quantum system as the nucleus. And the weak force can act whenever the electron's wave function and the proton's wave function overlap sufficiently. The rate of electron capture depends on several factors. It depends on how much the electron's wave function overlaps with the nucleus, which is greater for heavier atoms because the inner electrons are pulled closer to the nucleus by the stronger electromagnetic attraction of the higher nuclear charge. It depends on the energy difference between the parent and daughter nuclei, because a larger energy difference means the reaction is more energetically favorable and proceeds faster. And it depends on the specific nuclear structure, the arrangement of protons and neutrons and their quantum states, which determines whether the weak force transition is allowed by the rules of quantum mechanics. Some electron capture transitions are what physicists call allowed transitions, meaning they proceed relatively quickly because the quantum numbers of the initial and final states are well matched. Others are called forbidden transitions, not because they're truly impossible, but because they require the particles to change additional quantum properties like angular momentum, which makes the process less probable and therefore slower. A forbidden transition might have a half-life millions or billions of times longer than an allowed transition for a similar energy difference. The word forbidden in physics does not mean it cannot happen. It means it is heavily suppressed, occurring much less frequently than an allowed process would. The richness and subtlety of electron capture in different nuclei is one of the reasons nuclear physics is such a deep and complex field. Each nucleus is a unique quantum system with its own energy levels, its own arrangement of protons and neutrons, its own set of allowed and forbidden transitions. Predicting the exact rate of electron capture for a given nucleus requires detailed knowledge of the nuclear structure, the electron wave functions, and the weak force coupling constants. It is a formidable calculation that engages some of the most sophisticated theoretical and computational tools in modern physics. But the underlying principle is always the same. The nucleus provides the energy. The difference in binding energy between the parent and daughter nuclei supplies the missing mass energy needed to create the heavier neutron. Without the nucleus, without that energy reservoir, the transformation would be impossible for particles at rest. The nucleus is not just a spectator in this process, it is the enabler. It is the energy bank that funds the transaction. It is the reason this transformation can occur in atoms at all. And this brings us to a profound realization. The universe has built a mechanism for transforming protons into neutrons, but it has placed a lock on that mechanism. The lock is energy conservation. The key to that lock is nuclear binding energy. Only in specific nuclei, where the binding energy arithmetic works out favorably, can the lock be opened and the transformation proceed. In all other cases, the electron simply orbits the proton, forming an ordinary atom, and nothing dramatic happens. But there is another key. A key forged not in the quiet structure of atomic nuclei, but in the catastrophic violence of dying stars. In certain extreme environments, the electrons themselves carry so much energy that the mass gap between the neutron and the proton plus electron combination becomes irrelevant. The electrons arrive with enough kinetic energy to pay the full cost of the transformation, and they pay it in a torrent, not one atom at a time, but trillions upon trillions of times per second, in a cascade of electron capture so intense that it reshapes the very structure of matter. This is what happens in the collapsing core of a massive star. And it is where our story reaches its most dramatic moment. Because in those final moments before a star dies, this quiet quantum process, this subtle quark flip mediated by the feeblest of forces, becomes the engine of one of the most powerful events in the known universe. Everything we have explored so far has been building toward this. The mechanism of the weak force, the conservation laws that govern every particle interaction, the energy barrier that prevents free electrons and protons from merging spontaneously, the nuclear binding energy that unlocks electron capture inside certain unstable atoms. All of these ideas converge in one of the most extreme environments the universe has ever produced: the collapsing core of a massive dying star. And what happens there will show us that this quiet, microscopic quantum transformation, a single quark flipping from up to down inside a single proton, can reshape the fate of an entire star. It can turn a ball of iron into a ball of neutrons. It can trigger an explosion visible across billions of light years. And it can create an object so dense that a teaspoon of its material would weigh more than a mountain on Earth. Let us begin with the star itself. A massive star, one with a mass greater than roughly 8 times the mass of our Sun, lives a dramatic and relatively short life. While a star like our Sun will burn steadily for about 10 billion years, a massive star burns through its fuel in a few million years or even less. The more massive the star, the hotter its core, the faster it fuses its nuclear fuel, and the sooner it runs out. A star 25 times the mass of the Sun might live only 7 million years. That sounds like a long time by human standards, but it is an eye blink in cosmic terms. The universe is nearly 14 billion years old. A star that lives 7 million years occupies roughly 1/2000th of cosmic history. During its life, the massive star fuses progressively heavier elements in its core. It starts with hydrogen, fusing it into helium, just as our Sun does. This is the longest and most stable chapter of the star's life. For millions of years, the core burns hydrogen steadily, and the star shines brightly, a beacon of light and heat. The outward pressure from fusion balances the inward pull of gravity, and the star finds equilibrium. Everything seems stable. Everything seems permanent, but it is not. The hydrogen is being consumed, and eventually it runs out. When the hydrogen in the core is exhausted, the core has no energy source. Gravity, which has been waiting patiently all along, begins to win. The core contracts. As it compresses, it heats up. And when the temperature reaches roughly 100 million degrees, something new ignites. Helium, the ash left behind by hydrogen fusion, begins to fuse into carbon and oxygen. The star has found a second wind, but this chapter is shorter. Helium burning lasts only a few 100,000 years, a fraction of the time hydrogen burning lasted. The fuel is consumed faster because the temperatures are higher, the reactions are more demanding, and the star needs more energy every second to hold itself up against its own growing weight. When the helium runs out, the core contracts again. The temperature climbs higher. Carbon begins to fuse into neon and magnesium. This stage lasts only a few thousand years. Then the carbon is gone and the core contracts once more. Neon fuses into oxygen and magnesium. This lasts roughly a single year. Then oxygen fuses into silicon and sulfur, a stage measured in months. And finally, silicon fuses into iron. This last act of nuclear fusion lasts approximately 1 day. Think about that progression. Millions of years of hydrogen burning, hundreds of thousands of years of helium, thousands of years of carbon, a year of neon, months of oxygen, and 1 day of silicon. The star's life is accelerating toward its end with terrifying speed. Each stage is shorter than the last because each successive fuel is harder to ignite, releases less energy per reaction, and must be burned faster to sustain the star against gravity. The star is not just running out of fuel, it is running out of time. By its final day, the core is a frantic furnace, desperately fusing silicon into iron, buying one last handful of hours before the end. If you could somehow slice the star open during those final hours, you would see a structure like an onion. Concentric shells of different elements, each burning at different rates. An iron core at the center, surrounded by a shell of silicon, fusing into iron, surrounded by a shell of oxygen, surrounded by neon, surrounded by carbon, surrounded by helium, surrounded by hydrogen at the outermost edges. Each shell is a record of an earlier epoch in the star's life. The hydrogen on the outside is the fuel the star started with. The iron at the center is the final product. The star carries its entire history in its structure, layered from birth to death. And then it stops. Because iron is the end of the line. Remember the concept of nuclear binding energy. Iron 56 sits at the peak of the nuclear binding energy curve. It is at the bottom of the nuclear energy valley. Fusing elements lighter than iron releases energy, which is why fusion powers stars. Splitting elements heavier than iron also releases energy, which is why fission works in nuclear reactors and atomic weapons. But fusing iron does not release energy. It absorbs energy. Fusing iron would require you to put energy in rather than getting energy out. This means the star can no longer generate energy by fusing its core material. The nuclear furnace that has sustained the star against the crushing force of its own gravity for millions of years has suddenly gone out. There is no more fuel. There is nothing left to burn. The fire at the heart of the star has died. The iron core sits at the center of the star like an ash heap, at the center of a spent fire. It is roughly the size of Earth, perhaps slightly larger, but it contains roughly 1.5 times the mass of our Sun. It is extraordinarily dense, hundreds of millions of times denser than water, and it is supported against gravitational collapse, not by nuclear fusion, not by heat, but by something entirely different. A quantum mechanical effect called electron degeneracy pressure. To understand electron degeneracy pressure, you need to understand a fundamental rule of quantum mechanics called the Pauli exclusion principle, named after the same Wolfgang Pauli who first proposed the existence of the neutrino. The Pauli exclusion principle states that no two identical fermions can occupy the same quantum state at the same time and place. Electrons are fermions. This means that in any given volume of space, there is a limit to how many electrons you can pack in. You cannot squeeze them all into the lowest energy state. Once the lowest state is filled, the next electron must go into a higher energy state. As you pack more and more electrons into a smaller and smaller volume, they are forced into higher and higher energy states. They move faster and faster. And this creates a pressure, a quantum mechanical resistance to further compression that has nothing to do with temperature or thermal energy. It is purely a consequence of the Pauli exclusion principle. This electron degeneracy pressure is what holds up the iron core of the massive star. The core is so dense that its electrons have been squeezed into incredibly high energy states. They are moving at substantial fractions of the speed of light. And their resistance to being compressed further creates a pressure that pushes outward against gravity. For a time, this pressure is enough. The core sits in a precarious balance, gravity pulling inward, electron degeneracy pressure pushing outward. As long as the core remains below a critical mass known as the Chandrasekhar limit, roughly 1.4 times the mass of the Sun, this balance holds. But the star is still burning fuel in shells surrounding the iron core. Silicon is still fusing into iron in a shell just outside the core, raining iron ash down onto the core like volcanic debris piling onto a mountainside. The iron core is growing heavier, and it is approaching the Chandrasekhar limit. When the core's mass reaches this critical threshold, something catastrophic happens. Electron degeneracy pressure can no longer support the core against gravity. The balance fails, and the core begins to collapse. This is where electron capture becomes the dominant process in the universe's most violent transformation. As the core begins to contract, the density increases rapidly. The electrons, already at extremely high energies due to the Pauli exclusion principle, are squeezed into even higher energy states. Their energies climb far beyond the threshold needed to drive electron capture. Remember, in empty space, a free electron and a free proton cannot combine into a neutron, because the electron does not carry enough energy to create the heavier neutron. But inside the collapsing stellar core, the electrons are not free particles at rest. They are quantum mechanically compressed to energies of tens of mega electron volts, far exceeding the 0.782 mega electron volts needed to bridge the mass gap between the proton plus electron combination and the neutron. At these energies, the electrons have more than enough energy to force the transformation, and they do, in enormous numbers. Electrons begin slamming into the protons inside iron nuclei and other heavy nuclei in the core. The weak force mediates the interaction. Up quarks flip to down quarks. Protons become neutrons. Electrons become electron neutrinos. The reaction we described earlier, the same quiet quantum process that happens one atom at a time inside a beryllium-7 nucleus or a potassium-40 atom in your body, now occurs on a scale that is almost impossible to comprehend. The numbers are staggering. The collapsing stellar core contains roughly 10 to the 57th power particles. That is a 1 followed by 57 zeros. And electron capture begins occurring throughout this entire volume simultaneously. Not one reaction at a time, not 1,000, not 1,000,000. Trillions upon trillions of electron capture events per second, all happening at once, all converting protons into neutrons, all producing neutrinos that stream outward. And here is where the process feeds itself in a devastating chain reaction. Each time an electron is captured by a proton and converted into a neutrino, one electron is removed from the core. That electron was contributing to the electron degeneracy pressure that was supporting the core against gravity. With the electron gone, the pressure decreases slightly. With less pressure, the core compresses slightly more. With more compression, the remaining electrons are squeezed to even higher energies. At higher energies, electron capture becomes even more favorable. More electrons are captured, more pressure is lost, the core compresses further. The electrons reach higher energies, more capture occurs. This is a runaway feedback loop. Electron capture removes the very particles that were holding the core up. Each captured electron weakens the support structure that prevents collapse. The collapse accelerates the capture. The capture accelerates the collapse. The process feeds on itself with terrifying efficiency. It's a death spiral from which there is no return. The core, which had been roughly the size of Earth, collapses at speeds approaching 1/4 the speed of light. In less than a second, it contracts from roughly the size of Earth to a sphere only about 12 miles across. The density reaches values that are almost beyond comprehension, roughly 250 trillion times the density of water. At this density, the matter in the core is no longer anything you would recognize. It is no longer iron. It is no longer composed of individual atoms. The atoms have been completely destroyed by the compression. Their electrons have been captured. Their nuclei have been crushed together. What remains is a sea of neutrons, a fluid of nuclear matter where individual nuclei no longer exist as separate entities. This is the birth of a neutron star. A neutron star is the corpse of a massive star's core, compressed to nuclear density by gravity and stripped of its electrons by the very process we have been describing. It is roughly 12 miles in diameter. It contains roughly 1.5 to 2 times the mass of the Sun. And it is composed almost entirely of neutrons, the very neutrons that were created by electron capture during the collapse. A teaspoon of neutron star material would weigh roughly 4 billion tons on the surface of the Earth. If you could somehow scoop out a sugar cube-sized piece of a neutron star and drop it on Earth, it would weigh more than Mount Everest. This is how dense the matter becomes when electron capture strips away all the electrons and gravity crushes the remaining neutrons together as tightly as the strong nuclear force will allow. The neutron star is held up against further collapse by a new form of quantum mechanical pressure, neutron degeneracy pressure. Just as electron degeneracy pressure arises from the Pauli exclusion principle applied to electrons, neutron degeneracy pressure arises from the same principle applied to neutrons. Neutrons are also fermions. They cannot all be squeezed into the same quantum state. They resist further compression, and this resistance supports the neutron star against gravity. If the original core was too massive, even neutron degeneracy pressure fails, and the core collapses into a black hole. But for cores in the right mass range, a stable neutron star is the result. Now let us talk about the neutrinos, because the neutrinos produced during this collapse play an extraordinary role in the story. During the collapse, electron capture produces an enormous number of electron neutrinos, roughly 10 to the 58th power neutrinos, a number so large it dwarfs the number of stars in the observable universe. These neutrinos carry away an incredible amount of energy, roughly 99% of the total gravitational binding energy released during the collapse. That total energy is roughly 3 times 10 to the 46th power joules, a number that is almost meaningless in human terms. To put it in perspective, the Sun produces roughly 4 times 10 to the 26th power joules per second. The total neutrino energy released during a core collapse supernova is roughly 200 times greater than everything the Sun will radiate across its entire 10 billion year main sequence lifetime, all of it released in about 10 seconds. 99% of the energy of the collapse is carried away by neutrinos, not by light, not by the shockwave, not by the expanding debris, by neutrinos. The explosion you see when a supernova lights up the sky, as bright as an entire galaxy for a few weeks. That visible light represents only about 1% of the total energy. The neutrinos carry the rest. The supernova is, first and foremost, a neutrino event. In the early phases of the collapse, the neutrinos escape freely. The core is dense, but not yet dense enough to trap them. Neutrinos interact so weakly with matter that they stream outward through the collapsing core and the surrounding star essentially unimpeded. They carry away energy and lepton number, draining the core of electrons and the pressure they provided. But as the collapse progresses and the density climbs toward nuclear density, something remarkable happens. The core becomes so dense that even neutrinos cannot escape. Think about what that means. Neutrinos, the particles that can fly through a light year of solid lead without flinching, the particles that pass through the entire Earth as if it were not there, these ghost particles become trapped. The matter surrounding them has become so incomprehensibly dense that even their vanishingly small probability of interaction adds up. At densities exceeding roughly 10 to the 12th power grams per cubic centimeter, roughly 1 trillion times the density of water, the mean free path of a neutrino, the average distance it can travel before interacting with something, drops to less than the size of the collapsing core. The neutrinos are caught. They are still being produced by electron capture, but they can no longer stream freely outward. They bounce from interaction to interaction, slowly diffusing outward but unable to escape on the timescale of the collapse. This trapping has profound consequences. When the inner core reaches nuclear density, it suddenly stiffens. The neutrons resist further compression, and the inner core bounces. Like a rubber ball hitting a wall, the inner core rebounds, sending a shock wave outward through the still infalling outer core. This shock wave is the beginning of the supernova explosion. But the shock wave is in trouble almost immediately. As the shock wave plows outward through the infalling material, it collides with iron nuclei still raining down from the layers above. These collisions dissociate the iron nuclei, tearing them apart into individual protons and neutrons. Breaking apart iron nuclei absorbs energy, an enormous amount of energy, roughly the same energy that was released when those nuclei were forged in the first place. The shock wave is spending its energy just to destroy the material in its path. With each iron nucleus it tears apart, the shock wave weakens. It slows, it loses momentum. Within milliseconds, the shock wave stalls. It stops moving outward. It hangs in the infalling material, losing energy, weakening, threatening to die. If nothing rescues it, the shock wave will be swallowed by the continuing collapse. The outer layers of the star will fall inward. There will be no explosion, no supernova, no scattering of elements across space, just a quiet implosion, as the entire star collapses into darkness. For a critical fraction of a second, the fate of the star hangs in the balance. The shock wave stands still, caught between the infalling outer core above and the hot proto-neutron star below. Everything depends on what happens next. This is where the trapped neutrinos may save the explosion. Below the stalled shock wave, the newly formed proto-neutron star is unimaginably hot and dense. It is radiating neutrinos in all directions, neutrinos produced by the continuing electron capture and the extreme conditions of nuclear density matter. These neutrinos are slowly diffusing outward through the dense material, bouncing and scattering, gradually working their way toward the surface. Most of these neutrinos will eventually escape into space without depositing any significant energy. But a small fraction, perhaps 5 to 10%, interact with the material just behind the stalled shockwave. They collide with protons and neutrons in that region, transferring energy to them. This energy heats the material. It increases the thermal pressure behind the shockwave. It pushes. If enough neutrino energy is deposited in the right place at the right time, the shockwave is revived. It begins moving outward again, slowly at first, then faster. It gathers momentum. It plows through the remaining outer layers of the star, and eventually, It blows them apart in the supernova explosion. The outer layers are hurled into space at speeds of tens of thousands of kilometers per second, carrying with them the heavy elements forged during the star's life, and during the explosion itself, carbon, oxygen, silicon, iron, and elements even heavier, scattered across light years of space to become the raw material for new stars, new planets, and perhaps new life. This neutrino-driven mechanism is currently the leading theoretical explanation for how core collapse supernovae work. The details are still being refined through some of the most complex computer simulations in all of science. These simulations must simultaneously model gravity, nuclear physics, neutrino transport, fluid dynamics, and the weak force interactions we have been discussing, all in 3 dimensions, all at extreme densities and temperatures. They are among the most computationally demanding calculations humans have ever attempted. And they show that the outcome is delicate. A slightly different neutrino luminosity, a slightly different density profile, and the shockwave might not revive. The explosion might fail. The star might collapse silently into a black hole. The margin between a spectacular supernova and a quiet disappearance may be astonishingly thin. In 1987, a supernova was observed in the Large Magellanic Cloud, a satellite galaxy of the Milky Way about 168,000 light-years from Earth. This event, designated supernova 1987A, was the closest observed supernova since the invention of the telescope. And roughly 3 hours before the visible light from the explosion reached Earth, 2 neutrino detectors on opposite sides of the planet detected a burst of neutrinos. The Kami-Okande detector in Japan detected 12 neutrinos. The IMB detector in the United States detected 8, 20 neutrinos in total, out of the roughly 10 to the 58th power that were emitted. 20 neutrinos. That is all we caught. The rest of those 10 to the 58th power neutrinos passed through the Earth and everything on it without a trace. But those 20 neutrinos confirmed what theory had predicted. The core collapse was indeed a neutrino event. The neutrinos arrived before the light because they were produced deep in the collapsing core and escaped before the shockwave had time to blow through the outer layers of the star and produce visible light. Those 20 ghostly particles, born from the same electron capture process we have been discussing all along, traveled 168,000 light-years across intergalactic space to reach our detectors. They carried the signature of protons becoming neutrons, of electrons becoming neutrinos, of the weak force reshaping matter under the most extreme conditions imaginable. Let us step back now and see the full picture. Because the sweep of this story, from a single quark flip to the death of a star, is one of the most breathtaking connections in all of physics. It begins with 2 particles, an electron and a proton. Electromagnetism attracts them, but electromagnetism cannot change what they are. The weak force can change them, but only if enough energy is available. In empty space, the energy is not there. In certain atomic nuclei, differences in binding energy supply the missing energy, and electron capture occurs one atom at a time. Quietly, invisibly, in your bones, in rocks, in the core of the sun. But in the collapsing core of a massive star, the conditions change radically. Gravity compresses the core. Quantum mechanics forces the electrons to enormous energies. Those high-energy electrons have more than enough energy to drive the transformation. Electron capture begins in a torrent. Protons become neutrons. Electrons become neutrinos. Each capture removes an electron from the population that was supporting the core against gravity. The support weakens. The collapse accelerates. More captures occur. The feedback loop spirals toward catastrophe. In less than a second, the core transforms from a ball of iron, rich in protons and electrons, into a ball of neutrons. The electrons are gone, converted into neutrinos that carry away 99% of the collapse energy. The protons are gone, transformed into neutrons by the weak force. What remains is a neutron star, an object so dense that the matter within it has been squeezed to the density of an atomic nucleus, 12 miles across, 1.5 to 2 solar masses, supported only by the quantum mechanical refusal of neutrons to be compressed into the same state. And the neutrinos, those ghost particles produced by the same reaction, diffuse outward, deposit a fraction of their energy behind the stalled shockwave, and may be the very thing that triggers the explosion itself. The supernova, one of the most energetic events in the universe, may ultimately be powered by neutrinos, by particles so ghostly they can pass through a light year of solid lead without stopping. The weakest force in nature, acting through the most elusive particle in nature, drives the most violent event in the cosmos. There is something deeply awe-inspiring about this. The same physics operates at every scale. The same weak force interaction that transforms a potassium 40 atom in your body transforms the core of a dying star. The same W- boson exchange. The same quark flip from up to down. The same electron consumed. The same neutrino born. The same conservation laws satisfied. The same ledger balanced. The mechanism is identical. Only the scale is different. And consider what this transformation creates. The neutron-rich matter produced by electron capture in stellar cores does not just sit there as an inert remnant. Neutron stars are extraordinary objects. They have magnetic fields trillions of times stronger than Earth's. They can spin hundreds of times per second, sweeping beams of radiation across the cosmos like lighthouses. Some neutron stars merge with other neutron stars billions of years after their formation, and those mergers produce gravitational waves that ripple through the fabric of space-time. Those mergers also forge the heaviest elements in nature: gold, platinum, uranium, elements that could never be produced by ordinary stellar fusion. The gold in a ring on your finger was likely forged in the collision of two neutron stars, objects that were themselves created by the electron capture process we have spent this entire journey exploring. So the next time someone tells you that the weak force is weak, that it operates over distances too small to matter, that it involves particles too ghostly to detect, remember what it builds. Remember that this force, acting through virtual W bosons that exist for less than a billionth of a billionth of a billionth of a second, can transform the identity of matter itself. It can turn a proton into a neutron. It can remove the very pressure holding up a stellar core. It can trigger the collapse that creates the densest objects in the visible universe. And it can do all of this while satisfying every conservation law with flawless precision. An electron is forced into a proton. One quark changes flavor. A neutrino is born and flies away at nearly the speed of light. The proton is gone. The electron is gone. A neutron stands in their place. That is the answer to our question. That is what happens when an electron is forced into a proton. Not a merger. Not a simple combination. A transformation, a fundamental rewriting of what the matter is, carried out by the only force in the universe capable of such alchemy. And that single transformation, repeated beyond counting in the heart of a dying star, turns a core of iron into a sphere of neutrons, and sends a wave of neutrinos outward that carries more energy than the sun will produce in its entire lifetime. One small change, one quark flip, and the universe is never the same again. Right now, as you sit here, potassium-40 atoms in your body are performing this same transformation. Protons are becoming neutrons inside your own bones. Neutrinos are streaming out of you at nearly the speed of light, passing through the walls, through the earth, out into the cosmos. You are, at this moment, participating in the same physics that builds neutron stars and triggers supernovae. The scale is different, the consequences are quieter, but the mechanism is identical. The same W- boson, the same quark flip, the same conservation laws. You were connected through this one microscopic process to the most violent and creative events the universe has ever known. That connection is perhaps the most remarkable thing of all. Not just that electrons and protons can transform, not just that the weak force can rewrite the identity of matter, but that this transformation is woven into the fabric of everything. It operates in your body and in dying stars, in laboratory isotopes and in the cores of collapsing suns, in the quiet ticking of a geological clock and in the birth scream of a neutron star. One process, one mechanism, one small, subtle, endlessly consequential change. A quark flips, a neutrino flies, and the universe moves forward. Different from what it was an instant before, shaped at every scale by the quiet alchemy of the weakest force in nature.